Okay, so good afternoon, everyone. Today we are hosting Marek Szczepańczyk. Marek is a researcher at the Faculty of Physics at our university. Marek did his master here in Warsaw. Then he spent many years in the United States. He did a PhD there, a postdoc there, and then he returned to Warsaw. And we are very happy to listen about gravitational waves and also to host you during your birthday, because today is your birthday. So happy birthday to you.
Thank you.
So there was a special gift we already gave you. So we hope to have some birthday fun related to gravitational waves.
Exactly. And my flight a little bit twisted towards my birthday. So there will be like some gifts, not only for me, but also for you. So today I will talk about what I'm working on, which is basically searches for gravitational waves using unmodeled or model-independent searches. And first, before I just say what was already said, that I spent 5 years roughly in Arizona and Florida during my PhD, then 5 years in Florida, so here, and then I got a permanent position in Warsaw, and also I got a Polish returns grant. And my supervisor here, the inviting person, was Professor Lewandowski, so I want to also mention him. He passed away a few months ago, very, very suddenly. So first, I'll start from a general introduction to gravitational wave astrophysics. I'll talk about the current observing run. Then I have two cases for you. One is about searching for exceptional gravitational wave sources, and then specifically searches and the status of searches for gravitational waves from core collapse supernova. So let's go with the first, actually, with the introduction. A very quick overview. So in astronomy, we are measuring basically electromagnetic light, but in the gravitational wave astronomy, we are measuring so-called gravitational waves, which are the oscillation of space-time. And in order to generate these ripples of space-time, we need to have some asymmetry in the system. So if you have a pulsar that is rotating even really, really fast, it does not, if this is spherically symmetric, it does not emit gravitational waves. However, if you have like a small mountain, like a meter mountain, or you have like certain other like deformation, then you have emission of gravitational waves. So you need some so-called quadrupole emission. You need to have some aspherical mass energy movement. So if you think about compact binaries, which is like two black holes, it's a very, very efficient generators of gravitational waves. And we can roughly separate them into the sources of gravitational waves into like standard, like stellar mass black holes, and I would say exceptional. And I will talk about the exceptional later on. What do I mean? So a very quick introduction of to gravitational waves. What we measure are the oscillations of space-time. So if you have a gravitational wave coming into the screen, if you have two objects, and when the gravitational wave is passing, this physical distance between these two objects is changing. And in order to detect them, we don't have just two objects, but gravitational wave interferometers, which are basically made of a laser source, one test mass, second test mass, and basically a beam splitter. So you shoot a laser into a beam splitter, you split your light into two arms, and then the light is propagating. Part of the light is propagating all the way to one end, and the second part of the beam is propagating all the way to the other end. And then they are reflected, and then they go back to the beam splitter, and then recombine right here in the photodetector. And the detectors are usually, well, they are kept in the dark mode, meaning that the interference in this photodiode is destructive. So any deviation, if any light that starts to be visible, it's indication that the length of the arms are changing. And what we measure is basically this delta L, which is the change in one arm minus change in the other arm. And this is proportional to gravitational wave strain and the length of the detectors. That in LIGO detectors, this is 4 kilometers. In Virgo and KAGRA, this is 3 kilometers. And they have to be, these are very, very sensitive instruments, and they have to be far away as possible from human activities. And this is an example of the LIGO Hanford detector, straight on basically a desert. This is how the mirror looks at one of the ends, basically right here. And this is me. Like I was actually a fellow in Hanford, and basically I was able to be inside basically the instrument. It's like really, really cool. And there are a lot of sources of noise: trains coming, planes flying, like ground shaking, or even like some like unexpected glitches. So just to clarify, this is me. This is not me. And at the moment, we have a network of gravitational wave detectors. So gravitational waves are so weak that we have to be able to basically what we observe in the detector basically compare with something else. And we need to have at least 2 detectors to be able to make sure that what we observe is a real gravitational wave. And we have 2 detectors in the US, LIGO Livingston and LIGO Hanford. These are these 4-kilometer detectors. We have operating detector in Virgo, and we have a detector in KAGRA, Japan, that is also like getting upgraded, and hopefully it will start observing in a few months. And we have like a small detector, GO600, that is like a testing bed for LIGO. And also currently under construction, we have LIGO India, which is basically a copy of LIGO detectors. And the site is chosen. Basically, the construction started, and some of the equipment in the US are basically awaiting the boxes to be shipped. So hopefully before the end of this decade, we'll have the first observations from LIGO India. And let me also mention that we have also planned a detector in Australia, which will focus on high frequency emissions. So one of the big technical challenges in building the detectors is basically ground motion, and you have to have a lot of hardware to basically mitigate it. And in Australia, basically they don't want to deal with that. It's expensive and time consuming, and they will focus basically on the high frequency emission, which is like 2 kilohertz. So like 2 to 4 kilohertz in order to detect basically oscillations of neutron stars. So then we had already a few observing grounds. In 2015, we had the first observing ground when only LIGO was observing, and we detected binary black holes. And I was basically practically starting my PhD, so like it was like perfect moment. Then we had the second observing ground, and the biggest discovery was binary neutron star detection, the kilonova. Then we had the third observing ground when we also had KAGRA joining for a very small period with like small but some sensitivity, and we detected the most massive black hole by then, the intermediate mass black hole above 100 solar masses. And then we at this current observing ground when it is lasting for 2 years, and I will talk more just in a second. And one of the significant results is a search for gravitational waves from supernova 2023 IXF, and I will talk about that basically towards the end of the presentation. And this is a great testbed to look for some new gravitational wave search populations and a lot of stuff. So I cannot talk much about this observing ground because data is not public, but I can give just some hints. So the O4 is 2 years long, and it will last until around like June of next year, so half a year and more. And we had 181 gravitational wave candidates. We had one extra today. So this is roughly 3 gravitational waves per week. And we have so-called, we are running model-dependent searches, also known as matched filtering. And we have model-independent searches. And this is what I will be talking about. This is what I'm specializing. And model independents are focusing on so-called gravitational wave bursts. So bursts of gravitation of the signals, it can be binary black hole, it can be core collapse supernova, it can be like some glitching, anything that is producing gravitational wave. And if we have public alerts, then we have we say how significant it is. We provide what is the direction of the sky, and we provide some other properties. And here is a list of links to, if you are interested to basically look for much more information about how the run is going, what is the status, like all this sensitivity talks, like how sensitive we are to binary neutron stars, and so on. The PDFs are available somewhere, or
YouTube, but we can.
Okay, so yeah, but there will be like YouTube, right? Okay. So it will be available, and a small gift for me, as I said, there's like 181 events from the events that happened just today, which was basically super likely is binary black hole, so there's rather no electromagnetic counterpart. But what's significant is the sky location. I know maybe like for astronomy it's not like as great, but for the gravitational waves, and this is like a very well localized source. So that's something interesting that happened today. So yeah, these gravitational waves are when we have the observing run, we never know what we can detect. We can have surprises, and this is like really nice, nicely localized event. And last point. At the moment, we are in the advanced detector era, or the second generation detectors, but there's plans ahead to the third generation gravitational wave observatories. And Einstein Telescope is the European project. Cosmic Explorer is the American project. And just a few months ago, we had a collaboration meeting of Einstein Telescope here in Warsaw. And the big news is that before the news, in order to build this detector, there are like a lot of challenges. First one is we don't know exactly what will be the design, and the second, we don't know what is the location. Up to now, we had 2 sites, somewhere close to Maastricht, Netherlands, and then Sardinia in Italy. And the big news from this meeting is that we had the third site right beside the border of Poland, like 20 kilometers from Poland, a proposal to build a detector over there in Saxony. So this is also the team and some of the people that were in the local analysis committee are here in this room. That's so nice. And let me go to the first case. The search is for exceptional gravitational wave sources. And what do I mean for exceptional gravitational wave sources? So at the moment we have almost 300 gravitational wave detections, and practically all of them are binary black holes. And we are looking constantly for events that have certain interesting properties, something that is unique, and something that can teach us about the universe. And this unique, special, or exceptional gravitational wave sources likely will play an important role in exploring the universe. And what I mean is new gravitational wave source populations. So during O3, I said that we discovered intermediate mass black hole and opened a venue to observe very, very heavy binaries. We observed 2 or 3 events that have a very high mass ratio. So one black hole had a mass of I think 3 solar masses, and the other had 30-40 solar masses. So the ratio was 1 to 10. We had one event with a ratio of 1 to 4. So these are all exceptional events that teach us something new about the universe. So we are still searching. We are looking for compact binaries from with eccentric orbits, hyperbolic encounters when you have one black hole and flyby of the other. When we have a collision, head-on collision of black holes, we have subsolar, some very, very small mass binaries, this extreme mass ratio, and also the gravitational wave bursts, core collapse supernova, a pulsar, neutron star glitches, maybe cosmic strings someday. Another exceptional source would be a multi-messenger event. We already have a kilonova binary neutron star discovery, but we will have to have more. For example, we haven't detected yet that post-merger, we haven't detected what's happening with the matter after the merger. And also, we can have gravitational wave sources with where we can observe new phenomena, either some, say, high harmonics or precession, black hole formation, or maybe some features beyond GR, gravitational wave echo, when we have 2 compact objects that are not black holes, and they are emitting, when they collide, they are emitting gravitational waves. There's a standing wave moving between them. So that's something that we also are looking forward to. So given that, let me describe my basically tool, the searches that are model independent. And the prime algorithm is coherent waivers. This is a software that is using minimal or no assumptions on the source. So unlike a templated search, we need to have a very precise prediction from general relativity in order to basically filter the data and find gravitational waves. But in this case, we don't need that. And I will describe how it works just in a second. As I said, it uses minimal assumptions, meaning that if we have a binary black hole, basically the frequency is growing over time. We have basically a shear. And regardless how you model it, basically the frequency will grow over time. And this is a very, very minimalistic approach in order to detect, and it happens to be very, very effective. And coherent waivers detected, that's something that not many people know, that detected the very first gravitational wave back in 2015. and then detected intermediate mass black hole a few years later. And it detects regular gravitational waves together with this model-dependent template-based searches. And if you have a core collapse supernova, a galactic supernova, then this is the most sensitive algorithm to actually discover it. So how does it work? Basically, the data from gravitational wave detectors is basically this strain data. This is basically x of t, and then you transform it in a wavelength transform into like time frequency maps, so like two-dimensional time frequency maps. So you know how the energy behaves in time and frequency. So if you imagine a piano, if you do this type of transform, you see a straight line at a given frequency. So so we have a wavelength transform from our signal from each detector where we have available data, and then we basically add them together. So we have like two images that we add together. The noise adds incoherently, so like randomly, but the signal adds coherently. So you have an enhancement of the signal, and this way you become more sensitive. Instead of like looking for gravitational waves in each detector separately, you basically add them together, and then you enhance the signal. So you identify your event, and then you do like all the mathematical likelihood analysis, and then you do inverse transform, and you reconstruct the signal. And this is an example of the first gravitational wave detection from 2015, and this is how the signal looks. So like we have 300 hertz. We have a peak frequency around 150, 200 hertz, and you have like a pixel. So you know how the frequency is evolving over time. So this is a very, very nice, very strong, clean signal, and all the other stuff around was not, so it was removed. So now we have a pretty we can classify this model independent searches in few categories, from minimally modeled to completely unmodeled. So on the far side we have minimally modeled. So we assume that compact binaries merge up to around like 300 hertz. So we restrict our search up to 300 hertz. We have the chirping structure right here, and this is basically a search for binary black holes, binary neutron stars, or combination of black hole and neutron star. Then on the other far spectrum, we have unmodeled searches. So we don't know, in this search, we don't know what to expect. We can have glitching, pulsar glitching, we can have for collapse supernova, we can have some other explosions, cosmic strings, or stuff that is unknown. So whatever is coming to the detector we are picking up as a gravitational wave candidate. And we are searching not up to like 300 hertz, but up to like 2 kilohertz, so the most sensitive part of the detector. And this is an example of a collapse supernova, and I'll explain much more later on, about the physics of it. And then we have something that is like in between. So if we know that we're looking for compact binaries, but compact binary mergers, but there is no chirping structure. If we have intermediate mass black hole, this is an example of, this is how intermediate mass black hole looks. The peak frequency is like 60 hertz. and this is you have like a blob of energy in time frequency. So we have to use like something in between, and if we have eccentric binaries, so binaries with eccentric orbits, or we have hyperbolic encounters, extreme mass ratio, or head-on collision. This is basically the region somewhere between this unmodeled and minimally modeled search. This is where we'll be looking at. And then finally, yeah, we have, I already talked about low latency searches, like these are the real-time searches. So any time when we collect data, we immediately try to find the gravitational wave and send astronomers information publicly about where to look at it. And then searches for new phenomena, looking for high harmonics, deviations from GR, all sorts of stuff. Second gravitational wave polarization, even. So a very quick recap of the results that we published very recently, which is actually very, very relevant. I started to talk about eccentric binaries. And these are very interesting astrophysically. So when you have stellar evolution, then you're expecting that two black holes that are formed have, say, roughly like similar mass, and then they have a circular orbit. However, if you have a different scenario, like globular clusters, places where you can have like a lot of compact objects. If you have one black hole that is captured by the other, you can have eccentric orbits, and this is called dynamical formation. And we think that it could be one of the LVK discoveries. Like similarly, like we didn't know, but we were searching for intermediate mass black holes, and it happened to be that we found them like sooner than later. We think that maybe the next discovery, like on our model independent search site, is detecting these eccentric orbit binaries, and we basically, in our previous paper, we reanalyzed the data from the third observing crown, and we found 3 extra gravitational waves. They're consistent with stellar mass black holes, so it's not like something like super heavy, but one event has a large mass ratio, possibly dynamic formation. These are weak events, so we cannot say much for sure, but it's definitely something interesting. And also, other relevant paper that we published also is actually published the same day. Archive number is like 15191, and this is 192. So like one after the other. And we are comparing different models for that are modeling the waveforms for eccentric binaries. And here is like an example of an event when we have like 2 models with eccentricity of 0.5. Eccentricity goes from 0 to 1. So if we have eccentricity 0 is basically circular, and eccentricity 1 is a head-on collision. So this is a very high eccentricity, and the stream is very short. But in this case, you can see that there are already like deviations. So there's a lot of work on the theory side to basically model this eccentric binaries. Okay, so let me go to the second cake of today. Is core collapse supernova. So core collapse supernova are phenomena that is was gathering imagination of people for millennia. This is a nebula, so the remnant of a supernova from 2054, so from 1 century ago. And this is a Chinese scripture where it was actually written that, oh, there's a guest star appearing on the sky. It's actually, when I ask Chinese, they can still like read pieces of it. So this is a guest star happening on the sky. And we are expecting that there's 1 or 2 per century in our Milky Way, in our home, 1 or 2 supernova per century. And the last one that we know was like 300 years ago. So it's way like overdue. We are waiting for the next galactic supernova. And how does supernova work? So when you start burning fuel, so you take hydrogen and you burn it to heavier elements, to helium, all the way to iron. You have a creation of like an onion-shaped star, where the iron is at the very center. And if you have this iron core heavy enough, when it exceeds the so-called Chandrasekhar mass of 1.4 solar masses, then the electron pressure is not enough, and the gravity basically collapses this core. And if you can imagine, you start from an iron core of around like 2,000 kilometers, and it collapses down first to like 50, 100 kilometers, and then shrinks down even later, even further. And when you calculate the potential energy of this iron core, then it happens that astronomers observe only 1% of that energy. So if you take the ejecta, if you look at basically look at the ejecta, so all the matter that is basically pushed out, it is only 1% of that potential energy. So the question is where all that energy goes, and it happens that if you have if you're thinking about this iron core, if you have electrons that are basically squeezed, they are penetrating into the nucleus, and they are basically meeting protons, creating neutrons and neutrinos. And it happens that majority, 99% of that energy escapes basically freely with the neutrinos. And while we don't know why stars explode, the so-called explosion mechanism is unknown. We believe that neutrinos play a key role. We had a supernova 30 years ago in 1987, and we detected like 23 neutrinos from a supernova. So it confirms that there's a large neutrino production during an explosion, and we believe that when the neutrinos are leaving, some of them, like small percentage, will interact with matter, and that will create basically heating that will blow out the star. So this is a Cork supernova, and while we don't know when it happens, we can have some small predictions. So in 2019, when we were at the meeting with the community simulated Cork supernova in Fukuoka in Japan, some people made wishes and like, yeah, we wish to have supernova. Some people predicted that we will have it 2025-26. So hopefully this wish will happen, and we'll see supernova either this year or next year. Hopefully when the gravitational wave detectors are running. So please, Mother Nature, to hurry up. But yeah, like otherwise we don't know when it will happen. So how far are we from the detection? So to answer that, let's see at the plot how much energy is emitted in gravitational waves. In terms of the solar masses, on one side we have solar masses, in the other side we have Earth. The typical explosion energy is 10 to 51 ergs. So this is this energy of the ejecta, of the matter that was pushed out during the supernova explosion. And according to like many models, the spectrum looks roughly here, like here. So we expect the gravitational waves to peak around like 800, 1000 hertz, and the energy is roughly like 10 to minus 8 solar masses. So if you think about compact binaries are emitting gravitational waves at the level of 1 to 3 solar masses. So it's like they are very efficient. And the frequency range is somewhere here at like 100, 200, 300 hertz. So these are definitely like higher frequencies and much weaker. So how far we are? If we take the first two observing grounds, we have these two dots. We were able to constrain supernova model for the first time. This is basically assuming a very simple emission process. We don't know what's happening inside the supernova. We cannot find it from the astronomical observations, and basically the only way at the moment to constrain all these models is to look at gravitational wave data. So we were able to constrain it for the first time a few years ago. During the third observing run, we expanded the frequency range, and we were not able to like basically beat the constraints. But this observing run, 04, we had a pretty nice supernova that was nearby, and our constraint basically went down around like 1 order of magnitude. So this is still in the range of these like toy models, like semi-analytical models. But if you think about very extreme numerical models, when you have large deformations of the core, we are somewhere here in this region. So we are expecting that if we have during 05 something of an order of few megaparsecs, then we'll be able to start basically constraining the models that are numerical, extreme, but still something that is that could be useful. And all the way, if you have closer and closer supernova down to 10 kiloparsec, we'll be able to basically reach further the models and eventually have a detection of gravitational waves. So in order to detect gravitational wave, we need to have we need to really have a galactic supernova. So that's something that we are really waiting for. And the technique that is used to constrain the supernova, the supernova engine, are the optically targeted searches. So we are looking at the sky. We are looking at the astronomical data, and we look for gravitational. We are looking for core collapse supernovae that happened nearby. Within like say 20-30 megaparsecs, so like fairly close. And from the optical observations, we try to constrain the moment when we had a collapse, when we had gravitational wave emission, and based on this interpolation, we have like ranges of like several days, a week, or maybe like a day. So like the time, a period where we can look for gravitational wave bursts. And if we don't find it, then we say that okay, if we don't see gravitational wave emission, but we say we are reaching sensitivity with certain model, then we say that this model is not correct. So if we look at the realistic models, this is for models coming from the multi-dimensional simulation, like very, very heavy, very big simulations, like realistic simulations. We are roughly at the level of like 1 to like 10-ish kiloparsec. Basically, we are barely going beyond our Milky Way, beyond galactic center. It's the situation is a little bit better now with the O4 data, so we are still like pretty. If we have a galactic supernova, we don't know if we will detect a gravitational wave emission or not. Then this is the optically targeted search from the with O3 data. At the time, we didn't have any interesting, like any nearby supernova. Nearby meaning the furthest here, the closest during that time was at 16 megaparsecs, so it was still like pretty far away. And we basically did a detailed study. This is that's why it was published as a this search was published as a short author's paper when I was the main author, with anybody from LBK who wants to join. And we are able to do like very detailed study of constraining the gravitational wave emission, constraining the power or the luminosity. So how much energy is emitting in gravitational wave per unit of time. So the best constraint is like 10 to minus 4 with so this is a typical explosion emission 10 to 51 erg, so like almost 1 order of magnitude. And with the current results, we go even like 1 further. And for the power, it's also at the low frequency emission 10 to minus 4 solar masses per second. And finally, this supernova 2023 IXF. This is a paper that was published just like 2-3 months ago, like very recently. It's a special LBK paper, the second special LBK paper with the O4 data. And as I said, we are able to go 1 order of magnitude, in the gravitational wave energy constraint. In terms of core deformation, we are maybe roughly 2 orders of magnitude away from the most popular supernova, most energetic simulations. So like the biggest deformations that people are taking in the numerical models. So if we are lucky, we'll be able to constrain it even further, like reach this level during O5. And another result is basically another measure of deformation. If we have binary, if we have a pulsar neutron star with a small asymmetry, like if you have like long-lasting neutron star rotating, then this ellipticity parameter is like 10 to minus 8, 10 to minus 9, and here we are not able. We are at the level of around like 1, but still, core collapse supernova could produce something so asymmetric. And then there's a lot of work. So at the moment we are focusing on the detection. Okay, we need to have a galactic core collapse supernova, and with the optically targeted searches, we are systematically constraining ranges of models, but at the same time, the community is preparing for the detection and inferring the physical parameters. So if you think about the collapsed core, So this is, if you remember, the core that collapsed that is like 50 kilometers radius. It shrinks further over time for the first like roughly 1 second, making the matter denser and denser and producing stronger and stronger gravitational wave, like higher frequency emission of gravitational waves. And there's a lot of work to understand the evolution of this proto-neutron star that eventually will evolve into a neutron star. All this supernova work is very sensitive to the nuclear equation of state that we don't understand. So can we actually extract, can we understand nuclear equation of state from our detection? We can have also supernova kicks. So you can have a core that collapses, but then due to asymmetries, say through the emission of asymmetric neutrino emission, can be basically kicked out. And this is what we observe, like very fast neutron stars in the galaxy. So it's a real thing. Then like how shock is propagating, how it oscillates, or rotational properties of this core. Because if you have an iron core due to conservation of angular momentum, you have basically slowly rotating, and then if you collapse it, then basically it rotates like really fast. So what are the rotational properties of this core? So there's a lot of work that is going on now in the community to extract parameters, infer the physical information from a potential discovery. And finally, the announcement that I want to make. Core collapse supernova are the most challenging astronomical phenomena to model. Basically, all 4 fundamental forces play an important role. Neutrino transport, so you have a gigantic flux of neutrinos, and it's a very challenging to model. It's computationally super challenging, and some of the simulations can run for 1 year and cost even $1 million. So these are very expensive simulations. And I've been involved, basically I work on gravitational waves, but there is an ongoing discussion with the people simulating these sources in order to enhance our chances of detection and parameter estimation. And there was a workshop back in 2017 at Caltech when there was a lot of discussions on what we do if you have detection. For a few years, people were focused basically on compact binaries, but there's always the question, what is the next big thing? And yeah, like a lot of people think that maybe we'll have a supernova like as a next big gravitational wave source. And there will be a workshop in Warsaw that I'm organizing under LIGO-Virgo-KAGRA umbrella. It will be in the summer 2015, probably around the GR Amaldi meeting. So like sometime in July. So the dates are not yet set, but please stay tuned, and it will be great to have some larger representation. So we will have a lot of people from the we will have plenty of people from gravitational wave side, and have plenty of people on the those who are simulating this core collapse supernova. Okay, so as a summary, I just want to give you a message that supernova, we don't know why stars explode. This is so-called supernova problem. It's already a century when we know that supernovae are exploding stars, but we still don't know why they explode. And the gravitational waves that came from actually straight from the core can bring an answer. With the optically targeted searches, we are constraining systematically the core collapse supernova engine, and there is a lot of effort for parameter estimation. And we have a LBK workshop here in Warsaw in the summer, around like July 2025. Actually, I'll also add my slides on my webpage to anybody who will be also interested. So thank you very much.
Thank you, Marek, for your birthday cakes and knowledge that you passed to us. Any questions or comments? Question?
You mentioned IMVHs in regions of black holes. So what is the difference of the division in these?
So what is the main frequency range, right?
Yeah, why they? These are single IMVHs or they are in binaries?
Oh, so yeah. So this IMVH that we detected is basically like when you two black holes of like 70, 80 solar masses that collided, and we have like 130, 150 solar masses event. So it's like it passes the threshold of 100. So this is basically the final black hole. But if I remember, in the O3 data, we also had some very, very heavy events that I think some component masses was around 100. I don't remember, and they also not as significant. So this one was like 4.5 sigma, like something that we know this is a detection. For the other, yeah, it's not as strong. There's to noise ratio like fairly low, so we cannot make like very strong predictions.
Or? I have a question about the eccentric binaries that you mentioned, like the object. So how can you distinguish if the given eccentricity is the effect of dynamical formation or evolution of the system? Or you just assume that if you have if it's circular, well, if it's not circular, then it's a dynamical? No, it's not the case, right? So.
Yeah, that's we're kind of saying that if you have eccentricity, that is like a dynamic system, because if you have events coming from stellar evolution, basically they are losing energy to gravitational waves, and basically they circularize really, really quickly. So yeah. So that's something that you need to have basically fast enough emission in order to merge before they get circular. But yeah, that's it's something really, really hard to distinguish, because if you think about the frequency evolution, yeah, you can have strong emission, no emission, strong emission until they merge. So your signal, instead of being nice and chirpy, is basically pieces of the signal, and usually you just basically see only the last part. That if you see only that part, it can be eccentric binary, it can be intermediate mass black hole, or anything that can have. So it's actually something that is very, very challenging to say for sure that what we see is actually eccentric. If we have in terms of the masses, we have light masses like neutron stars collision, and then intermediate mass black hole. And basically, the mass scales with the frequency. So this is a very strong indicator. If you have a very low frequency signal, then it's an indicator that this is heavy binary. But for the eccentric binary, we can have higher modes. We can if we have the few pieces. This is also a strong indicator, but yeah, the signal overall has to be strong.
Thank you.
So yeah, this is more challenging actually to detect than say intermediate mass black holes.
On the map of all the detectors, they were on the north hemisphere, and none was on the south. is it a problem for localizing events, or this distribution on Earth is completely sufficient?
Yeah, so this is a good question. Basically the answer is that when the gravitational wave is passing through Earth, it doesn't interact with matter. The interaction is like so weak that it's not changed. So it doesn't matter if this is coming from the north or from the south. If it goes going to trace through the atmosphere through the whole Earth, basically the signal is unchanged. So it doesn't matter if this is if the detectors are at the north or south. For the sky localization, it matters, and the further detector, basically the better, because if you think about how we actually detect the sky location, basically it's like in radio, that if you have two detectors, say at the at the top and bottom, if you have detection coming gravitational wave passing from the top, then you hit first detector, then you hit the second detector. If you have gravitational wave passing from the side, it's basically the wave is hitting the detector at the same time. So from whatever direction you look, you either hit you hit detectors one after the other, and that's you can basically find like a circle on the sky due to the time delay. So for Hanford and Livingston, it's like 10 milliseconds. For Hanford and Virgo, if I remember, like 27 milliseconds. So if you have something that is in Australia, Africa, or South America, it will be like more. So that will be like something nice. But already like 30 milliseconds is like strong enough. And then if we have the third detector, basically we pick up, actually this event is actually a nice example. We have basically circle the sky. This is only with two detectors, Hanford and Livingston. So we have circle the sky, like we have to say like this is basically the location. If we have the third detector, Virgo, then it would be constrained to like very small patch on the sky. So basically, the more detectors we have, the better sky location we have. But it doesn't, it doesn't fully help whether we have detector at the north or southern hemisphere. It's rather like the number of the detectors. Mm-hmm.
I think we don't have anything online. Łukasz, can you take a look? Questions or comments on Zoom? No, nothing. So thank you very much. Happy birthday.
Thank you.
And next week we have Surajit talking about fast radio bursts, right? So, thank you.